in here. All right. So we finished up with time-invariant predictors, except I had a question over break. Is it possible to have a level 2 interaction of age by reasoning? Sure. Why didn't we have one? Because I didn't think we'd have time. That's the honest answer. But in my regular course, I do have an example with that on these same data. So this is a piecewise model that actually fits better for the same 6-session response time data in which I added age by reasoning. So because age and reasoning are both level 2 predictors, their interaction goes into the level 2 model. So gamma 03 is what I would call like the main effect of age by reasoning. You can think of it as how age and reasoning modify the intercept, either over additively or under additively. Likewise, gamma 13 is age by reasoning by time, where time is slope 1, 2, and gamma 23 is age by reasoning by slope 2, 6. So yes, absolutely you can fit interactions among level 2 predictors. In practice, somewhere between testing everything possible and testing only the stuff you care about is what I would recommend. I can't give you any more specific guidance than that as to how deep you should go. One thing to keep in mind, though, when you get the output back, whenever you have a two-way interaction among level 2 predictors like this, each of the predictors is then conditional on the other. So in addition to everything being conditional on time, these effects of age in this output, given the interaction of age and reasoning down here, these effects of age are specifically for someone with average reasoning. These effects of reasoning are specifically for an 80-year-old. And then these terms talk about how reasoning changes the effects of age, or how age changes the effects of reasoning. So we can do an example of how to do this, because what we're talking about is how to interpret 2- and 3-way interactions. The same rules apply to a 3-way interaction. It makes the 2 ways more positive, less positive, more negative, or less negative. So if I go, let's say, age first, here's the main effect of age. So older you are, the slower you are at time 0, excuse me. So what's this pattern right here? If age is my slope and reasoning is my moderator, what does reasoning do to my age slope? Got a positive age slope and a negative interaction with reasoning. Less positive, yep. For every additional unit of reasoning, this age slope becomes less positive by about a point. I can go the other way. Here's my reasoning simple main effect, specifically for an 80-year-old. That's a negative main effect of reasoning, a negative interaction with age. So this is a more negative, yep. So the older you are, the stronger the effect of reasoning. So a more answer, more negative or more positive, makes the effect stronger as the interacting variable increases. A less answer makes it weaker. And we can do the same thing for the slope. So here's slope 1, 2. This is the difference between session 1 and session 2 for an 80-year-old with average reasoning. What happens to that negative slope in older people? Just look at the coefficients. Don't worry about the p-values. What happens to the slope for 1, 2 in older people? More negative. Now let's layer on this. This 3-way interaction takes this 2-way interaction and makes it less negative. So if I were going for English here, I would say something like, the extent to which older people change more is diminished in people with greater reasoning. Say that again. The extent to which older people change more, that's getting me up to here, this age by slope, is diminished, is less negative, in people with higher reasoning. that two-way interaction becomes less negative by 1.2 for every unit reasoning. If I go this one, let's do here. Yeah, let's go that way. Let's go slope 2/6 and slope 2/6 by reasoning, and then slope 2/6 by age by reasoning. So slope 2/6 is the rate of change per session between sessions 2 and 6. That rate of change is what in people with higher reasoning? Less negative, yeah, diminished. And what does age do to that two-way interaction? Positive two-way, positive three-way. More positive. So putting that together, the extent to which smarter people change less is exacerbated by age? Yeah, see? I took the GRE too. You don't want to know what my verbal score was. But they still let me in, and I'm here to prove that the GRE matters little. So yeah, the extent to which faster people change less is enhanced, is exacerbated, is made stronger in older people. The extent to which smarter people change less. I think I said that. Sorry. Need to reload. So I've had people shy away from interactions because they're too hard. They're not. You just got to find the pattern and then make a picture. So depending on what you think the moderator here is, if age is your moderator, I would do slopes by various levels of reasoning in young people and in old people. If reasoning is your moderator, I would do slopes as a function of age for low and high reasoning. And then you can walk your reader through what these things mean, should they be significant. So yeah, this is why Chapter 2 of my book is all about interaction terms, because I got to this point in the course several times and people were like crying. They had never seen three-way interactions and didn't know what to do with them, so I thought we got to tackle that first before we tack on the longitudinal component. So this is example 7 from my fall class 944 at KU. So yeah, we've officially reached the end of the fall semester, folks. That's where we're at right now. So congratulations. You all get an A. Okay. So that was that question. We also had a question about time varying. Should we do that one next? Why not, right? Or do you want to do power next? No. Time varying? Yeah. All right. Thank you for having an opinion. Freebird! So lecture 3 in 945 is where I am. So let me find my website here. So ask the Google for LesaHoffman.com. There I am. There's the picture that we took at Sears a decade ago when I realized I needed a professional picture. I hate having my picture taken, but I knew I needed one. So this is the picture that shows up everywhere, and it is close enough to what I look like to be serviceable. My hair has changed length several times, but this one is actually reasonably accurate. So there I am. Course materials, 945 and 944 are the courses we just finished. So I'm at the top of 945. Lecture 3 is what I'm pulling up here. And yes, I have videos for all of this unless I forgot to hit record or my microphone died. One of the two, that sometimes happens. I think I'm recording. Yeah, I'm recording. Okay, good. So lecture 3, time-varying predictors of within-person fluctuation. So I'll do a little bit from this, and then I'll do a little bit from lecture 9. So here we are. So time-varying predictors then. Whether or not you are focused on within-person change or fluctuation, at this point we will have already put in all effects of time that you need to have. So even if you started out with change, what's left is without consideration of time. The residuals should not have any timeness to them. It should already be built into the model. So time is irrelevant. What we're looking at is where you are on an outcome and a predictor at the same occasion, regardless of which occasion it is. So we're looking at level 1 predictors predicting level 1 residual variance. However, the reason this topic takes a month and took a whole lot of space in chapters 8 and 9 of the book is that time-varying predictors are almost always person predictors too. There is almost always between-person variance in X and within-person variance in X, and we have to be able to differentiate the effects of these two different sources of variance. And when the model only has fluctuation for the time-varying predictors, we only have to worry about these two. When the model has change in it, that's when we have to worry about slope variance as well, and so that's why I have lecture 9 that sort of follows up on this idea. So let's say, for example, within-person variation in stress, we might collect stress every day of the week, and we will find out that some days are worse than others. That was why we asked them every single day. And some people will say that they have more stress on average than others. So to the extent that you can take this stress predictor, calculate its intraclass correlation, just as if it were a time-varying outcome, we can see how much of its variance is between versus within. So if I have an intraclass correlation for a time-varying predictor that is greater than 0, we know that it has at least some between-person variance in it. Even though you're thinking of it as time-varying, it is also people-varying. And that people variance could have a between-person effect that captures random intercept variance. To the extent that the intraclass correlation is less than 1, the time-varying predictor does indeed have level 1 within-person variance, and so it can have a within-person effect. So if you think about the predictors that we've looked at so far, if I were to take a time-invariant predictor and try to estimate an intraclass correlation for it, what would it be? It's either 1 or 0. Which is it? It's a 1. Yeah, it's a 1. A time-invariant predictor is all between. It's all between. So all it can do is be a between effect. In our example, we also had time that was perfectly balanced and where everybody had the same intervals. There was no between-person variance in time. So its intraclass correlation was 0, which means it could only have within-person effect because it only had within-person variance. So the predictors we've seen so far are special cases where they're purely at one level or the other. That rarely happens for predictors that are measured for other types of things over time. So then the question is, how do you not screw this up? So the effects between persons and within persons could be in the same direction or they could be in different directions. So it may be the case that people with more stress have worse health, and it may be the case that when you feel more stress than usual, you feel worse than usual. If you look at exercise and blood pressure, people who exercise more have lower blood pressure because it's an index of health, whereas when you're actually moving, your blood pressure increases relative to when you're sitting still. So those are both true things. What blood pressure means differs across levels, and the effect that it has differs across levels. And for no other reason, these variables are on different scales. Unless your intraclass correlation for y and x are both 0.5, your estimates for their between effects are going to be different from their within effects purely because they are unstandardized regression coefficients, for that reason alone. So in these models, there are 3 potential kinds of effects that you would want to worry about when you have time-varying predictors that fluctuate over time, so that do not change systematically with time. There's level 2 between, there's level 1 within, and then there's this other thing that gives people headaches that I've grayed out for right now. So here's how we're going to get at each of these sources. We're going to take what was my time-varying predictor, xti, and we're going to compute the person mean across time. The person mean is centered at a constant so that 0 means something. What happens at level 1 then? You've got 2 choices. What is called group mean centering in clustered data is called person mean centering in longitudinal. There's grand mean centering, or just using a constant instead of a variable. So these choices do not apply to what level 2x is. Level 2x is always person mean, but these differences, which one you pick, changes what the interpretation of what person mean x is. So this gets ugly quickly. I will show you person mean centering because that's what I like best, because it's easiest. So we're going to carve up the original time-varying predictor and make two new predictors that go into the model instead. Person mean x is the person mean centered at a constant. So if I pick the sample mean, then a positive value of person mean x means I have more of this predictor on average than other people. A negative value means I have less than other people. Within person x, then, is the original time-varying predictor minus the person's mean. I am centering at a variable, not a constant. So within person x is 0 when I'm at my mean. If I have more of it than my usual, it's positive. Whatever usual is up here in level 2 in green. So here's what a model would look like. In this instance, we don't have time in the model, so this would be a case of pure fluctuation. So I have within person x at level 1 and person mean x at level 2. And you'll see why I like this. We have carved these variables up into level-specific variables. So within person x has only level 1 within person variation. Therefore, its effect can only be the level 1 within person effect. Likewise, person mean x is a time-invariant predictor. It has only level 2 between variation, and so the only effect that it can have is a level 2 between effect. The end. They're orthogonal. Each does its own job. It's a lovely division of labor. So in longitudinal data, I almost always set it up this way because it virtually guarantees you're not going to screw up the interpretation of these coefficients. The level 1 within is the effect of having more than usual. The level 2 person mean is the effect of having more than others. So what I've done essentially here, graphically, is take my x and divide it into a level 2 variable and a level 1 variable, in the same way that the model took my original time-varying outcome and divided it into random intercept variance, that's level 2, and residual variance, that's level 1. And when you look at it this way, you might say, why are there boxes on one side and circles on the other? Doesn't that seem arbitrary? To fix that requires multivariate models, or what people call multi-level SEM. But what we have done is like the poor man's model here. We have tried to approximate what would be random intercept variance in a model by making a level 2 observed person mean variable. And we have tried to approximate what would have been level 1 residual within variance by making a level 1 observed variable. So here's some pictures. This is the relationship between stress on the x-axis and let's call it disease severity on the y-axis. Pick your favorite disease. And these are slopes for different people. Oh, my podium is not working here. Okay. So the yellow dotted line is the slope through the person means. That's my between person effect. So that coefficient is 1 in this picture. The individual lines are for different people, and they have a flat slope of 0. That shows that they have no within person effect whatsoever. If you did a longitudinal study and this was your result, you would probably cry because it means you wasted your time. It doesn't matter if you have more stress than usual. You don't feel worse than usual. All that matters is if you have more stress on average than other people, you feel worse on average than other people. The opposite would be this. Camera 1, camera 2. Camera 1, camera 2. Now, if this was your result, you would have a publication in like Health Psych or something, because now it doesn't matter how much stress you have relative to other people. There's no between effect. It's all within. Or you could have both. Both matter to some extent, although to different extents. Or you could go crazy and actually have an interaction term between the two. So I can add person mean x as a predictor of my within person x effect. And going with it then would be a random slope for the within person effect of x. So this is a different way of thinking about what a random slope means. Before, it was each person needed their own effective time. Now it's each person needs their own effective stress. The extent to which stress than usual, feeling worse than usual, differs across people. That's this U1 variance right here. Part of the reason that it differs across people might be just how much stress you have in an absolute sense. That's person mean stress. So this is a cross-level interaction between the parts of the same variable. And that would look something like this. Here is an underadditive interaction, a negative interaction. So the between effect is specifically through the means. The within effect is centered for a reference person of mean stress here. And what the interaction term says is that for every unit higher person mean stress, the within person slope becomes less negative by 0.5. So having more stress than usual matters less if you already have a ton of stress to begin with. I call this the undergrad effect, right? When you're young and you have really no troubles, everything is a big deal, right? And then you hit graduate school and the tenure track, and it's like, what now? What? Okay, fine, whatever. I can handle it. Go ahead and throw it at me. People become resilient when faced with lots and lots of challenges. So there's a lot of things stress could do here. Yes, sir? That one. This one? You could add it, and that would be a logical precursor to adding any cross-level interactions here. It would be a likelihood ratio test, the same as adding any other kind of random slope. No, I didn't say that. I would do it one at a time. Is there an effective stress on average, and then does each person need their own within-person effective stress as two separate questions? If they need their own effective stress, why? Would then enable predictors right here to explain why that is. So most people screw this up. What most people do is commit the cardinal sin I refer to in the book as smushing. Not to be confused with what it's called on Jersey Shore, what workshop participants once told me. I will not repeat here, but it's not that. So time-varying predictors the other way here. In addition to between and within effects, there is another effect that we can't get directly out of the model but is implied by the model, which is whether or not these between and within effects are the same. Another way of saying this is there a contextual effect? After controlling for the absolute amount of stress on a given day, what is the extra effect of being a stressed out person? Extra is the key here. So within plus contextual equals between. Any one model gives you 2 out of the 3 directly, and you can get the third via an estimate statement. But you can rephrase the model to get this contextual effect instead by switching to grand mean centering for your time-varying predictor instead of person mean centering. So here is what happens. Do you remember in regression how when you stick predictors in the same model, they become the unique effect controlling for the other when they're correlated? Well, the same thing's going to happen here. So let's say that I've got 2 rows of data for 2 different people. The first person has a person mean of 3 and a second one has a mean of 7. If I center that at 5, there's my new variable. Person mean x goes in the model. Here's their original data. What I showed you first is person mean centering would create these scores. So they're 1 unit lower than average or 1 unit above average. But what average is gone. All between person information is gone. It's over here. In grand mean centering, it's both relative within person information and the between information is still here. So this level 1 variable is actually level 1 and level 2 both, whereas this level 2 variable is level 2. So they're going to have different effects in the model when they're by their own selves, as my son would say, than when they're separate, or when they're combined, excuse me. So here is what not to do. Don't smush it. This is the most common thing. You see this all the time, and it is very, very wrong. So just stick in the level 1 predictor, center it maybe, but don't just stick it in all by itself. This thing has both level 2 and level 1 variation, so its fixed effect is what I call smush. It is a combination of the within and between effects. If you'd like to sound a little more sophisticated, you can call it a convergence effect or a conflated effect. I like conflated. That's a Chris Preacher term. I like that one too. But the point is that this is 2 variables, not 1. This is person differences in stress and within person variation in stress. It's 2 variables, but you only gave it 1 fixed effect. So that fixed effect has to do the work of 2 variables. It can't be right unless those 2 effects really are the same. So this is bad. How to fix it? So this is what it looks like here. You're allowing 1 fixed effect to do the work of the between part and the within part. This only works if those 2 fixed effects are the same, which hardly ever happens. How to fix it then is to stick in person mean x. And this is where the interpretation gets tricky. You have to think of these coefficients as after controlling for the other. So time varying x has both level 2 between and level 1 within. Person mean x has only level 2. So what is the unique effect of time varying x going to be? What does it have that person mean x doesn't? Level 1. So we end up at the same place as using person mean centering with respect to the level 1 coefficient. It becomes purely within after statistical partialing on the part of the model. Now you would think then that this person mean x, because it is purely level 2, should be the between effect, right? Nope. Because part of its effect is over here in the level 1 coefficient. So it picks up the contextual effect, the difference of the between and within effects. So graphically it looks like this. My level 1x has the within effect, but it also has level 2 variance in it that's carrying part of the between effect. The level 2 person mean picks up the extra part that it needs to get to the full between effect. So why this matters is because in certain packages such as M+, sometimes you get the contextual effect at level 2, sometimes you get the between effect, and sometimes you get a mixture of the 2. It all depends on exactly how you write the syntax. So this is the big difference. The full between effect is the effect of being, say, a more stressed out person. The contextual effect is the additive effect of being a more stressed out person after controlling for how stressed out you are today. This makes a little sense in longitudinal data. It makes a whole lot more sense in clustered data. In clustered data, the contextual effect is the extra effect of the group after controlling for individual characteristics. That makes much more sense. In longitudinal data, a time is not a thing. A time doesn't have a characteristic in the same way that a person within a group has a set of characteristics. So contextual effects, to me, make little sense. And here's some math that you can rearrange these models and get to the same place. And you can't smush interaction terms either, so that's what the rest of this is about. More math showing what happens when you add interaction terms. When you add random effects, they're not the same. The fixed effects are close but not the same. So That's the tricky part here with these interpretations. How is that? So I have lots of examples of time-varying predictors. Now, where you can't do that anymore, this is Lecture 9 in the same class. So we started out reviewing what we just went over. Level 1 predictor can be created in two ways. Here's the within-person version, that's person mean centering, or what I call variable-based centering more generally. Level 1 predictor can also be just centered. When you pair the person mean x with the within-person version, person mean x carries the total between effect. When you pair it with the original predictor, it carries the contextual effect instead. So there's the smush diagram. There's the contextual effect diagram. Here's person mean centering because it's much easier to understand. No matter what happens, level 2 person mean carries the between effect at the end. No matter what happens, this within person variable carries the level 1 effect at the end, and you can write an estimate statement if you want to get the contextual effect for the difference. So what if we did this instead? Here. Camera 1, camera 2. Spot the difference? Let's let the model figure it out instead of us. Instead of carving up this x into its level 2 and level 1 components and treating them as perfectly observed variables, let's let the model do it. Let's make it on the same as y. So this is what some would call multi-level structural equation modeling, and what I call multivariate multi-level. Why it is called multi-level SEM is because people think of these random intercepts as latent variables. But I hate that term when applied to this type of model because there's no measurement here. These aren't latent factors. This is an observed x with its level 2 and level 1 variance. There's nothing different about this. So it's unfair to me to use the term SEM when you don't have a measurement model. That being said, it is possible to fit measurement models that are multi-level models. You can have within and between factors, and that would be truly multi-level structural equation modeling. So there's some literature on whether or not this is necessarily worse than this. It turns out that some of the problems in doing it this way, there's only EML, so this doesn't work as well for small samples. When you try to fit interaction terms, so if I wanted to have this between person variance interact with some other variable, that creates a latent variable interaction instead of an observed variable interaction, which requires numeric integration to solve. So I have a couple notes on here about the pros and cons of each of these things. If you have time-varying predictors that show individual differences in change, then you cannot do person mean centering or any other kind of observed variable version of a time-varying covariate without getting it some kind of wrong. Because what you're thinking of as between versus within is incomplete. There's at least two kinds of between. There's intercept and there's slope. And so what you really need is something like this. If your time-varying predictor has individual change and your time-varying outcome has individual change, each of those needs to have that change variance in the model at level 2 because it can have its own effect. So some would call this a bivariate latent growth curve model. The idea is that you have intercept relationships, slope relationships, as well as residual relationships. If you're happy making these relationships out of covariances, you can trick mixed into doing this kind of model. But if you want to have one predict the other, that's when you need either SEM or multivariate, multi-level in M+. So that's the rest of the story then is how to actually estimate those models. How's that? Questions on that or parts of that that you want to hear again? Or if you want to hear how it applies to you? So no smushing. That's the cardinal sin, smushing. Sticking in level 1 effects without considering their level 2 variance as a separate predictor. No questions? No. Had another question about how all of this applies to non-normal outcomes. It does. Everything I had to say so far applies to predicting binary outcomes or ordinal outcomes or anything else. A couple caveats, though. When you have a distribution that does not have a separately estimated residual variance, such as Bernoulli for binary data, there is no residual variance, or a binomial, then you can't have a level 1 variance that goes down when you add predictors. So that causes the model to change scale instead as you add predictors, because it's going to stay at whatever the variance is that goes with the link function, such as 3.29. The other trick to those models is that they're much harder to estimate because they require numeric integration. So that's the process of trying to integrate out all the random effects so that they can figure out what the conditional likelihood would be. And it's the same problem in, say, multidimensional IRT models that cause things to blow up and people switch to limited information. So it can be hard to estimate random effects for non-normal outcomes in multi-level models. But otherwise, everything proceeds relatively the same. And I have a couple examples using Glimix, M+, and Stata in this same course doing some of those models. No questions? Okay. So at this point, I can talk about power stuff, or I could move on to the crossed random effect stuff that I had planned. Do you have an opinion? You vote for power. Yeah? Someone's like, please speak up for us. Yeah, I know you're all afraid of irritating your friends here. But so power analysis is, quite frankly, a whole lot of creative writing. It is possible to make it look like you've got enough power to do whatever you want if you're creative enough. That being said, you do have to get used to providing power estimates for grants, for dissertation proposals, and that kind of thing. A lot of times people come to me and say, I need to do a power analysis. And my first question is, power for what? Power for what is always the question, because your estimate is going to be different if you're trying to power, say, a level 2 main effect versus a cross-level interaction versus a random slope variance versus whatever. So you have to be very specific in what you're trying to power. There's some easy ways to think about how to power main effects, and this is what's in Chapter 13 of the book. Let me get out an example based on design effects and effective sample size. Let's see, who would I have helped with that most recently? Someone named Katie. Let me get out her spreadsheet. So this is a student who came to me wanting to know how many people she needed. So she has level 1 predictors that she's trying to power. So what you need to know to try and figure out power for level 1 main effects. The issue is, what is your actual sample size going to be? Because you would think, say for instance, she has 18 occasions. This is an intensive measurement design on 20 people. That's 360 observations. So you would think, well, for a level 1 predictor, she has 360 observations. That's really good, right? Level 1 is nested in level 2, though. So you have to figure out what that nesting does to your actual amount of information in those 360 observations. So the best case scenario is if you have an interclass correlation of occasions from the same person of 0. So that creates a design effect, which is an indication basically of how screwed you are by your clustering. That's the easiest way to think about it. The formula for the design effect here is 1 plus the interclass correlation times the number of occasions minus 1. Shows it right there. So if your ICC is 0, your design effect is 1, which means you take your actual sample size, divide it by the design effect, and you get your effective sample size. So if occasions from the same person have nothing to do with each other, she can think of these 360 observations as independent. And she does have power at the level of 360. Well, I had her go and try to figure out what a reasonable guess for an interclass correlation was, and she came back with 0.6. Row. Now I have a design effect of 11. So that means she needs 11 times as many observations as she would if these data were truly independent. So she goes from an actual sample size of 360 to an effective sample size of 32 observations. So to power main effects, what you would want to do is, based on your planned number of occasions and your number of people, get a range of interclass correlations that is plausible. So I might also do like 0.5, for instance, and say 0.7, make that 20. And if these parameters were locked, 18 occasions and 20 people, I might say, well, based on an interclass correlation of between 0.5 and 0.7, my effective sample size is going to be somewhere between 27 and 37. If that's not enough, then I need to go get more observations. But whether it should be more occasions or more persons, it should be more persons, even if it's level 1. So if I increase, say, the number of persons here, let's go 25. Let me make these equal, 0.5 here. Let's increase this 5, that'd be 23. I get a bigger hit from getting 5 more people than I do 5 more occasions from the same people. I'm up to 47 versus 47 versus 38. And that's because this design effect is a function of not only interclass correlation, but the number of occasions per person. The more occasions you have per person, the less each one counts as an independent piece of information. So to power main effects, then, what I would do is figure out how many actual observations you need to get to an effective sample size that's going to have adequate power. And from there, you can look at like the classic Cohen stuff, get your D's and your R's, and be like, okay, well, here's my sample size. I've got 80% power. I have actually a sheet that I made for my very first class as a TA in graduate school that I probably refer to once a week. I think it's on my website, but if not, I can send that to you as well. It's a power table that I made out of the Cohen 98 book. So for instance, if I know that I'm looking at somewhere around like 30 to 40 as my effective sample size, that gives me, here's my power equals 0.8. That gives me a D of about 0.65-ish. So that's good for mean differences. If I'm thinking of it in terms of a continuous predictor and I want to think in terms of like a correlation, power of 0.8 is, 0.45 or so for an R. So for main effects, that's how I'd approach it. For level 1, you need to correct the number of level 1 observations for the design effect, which is a function of the interclass correlation, and the number of occasions per person. So the effective sample size will be somewhere between, worst case scenario, interclass correlation of 1, and your level 1 sample size is your level 2 sample size. Best case scenario is an interclass correlation of 0, which means your actual sample size is your effective sample size. So somewhere between level 2 and level 1 is what you're going to end up with in effective based on the size of your interclass correlation and the number of occasions. So this is, in Chapter 13, I walk through this sort of calculation in the context of 2-level and 3-level data. So questions on that? So then to power random slopes. That's harder. I totally punted on that in the book. I have a paragraph that's like, it's hard. I just see this other people's stuff. I'm not doing it. But then I had to start writing more grant proposals. So I had to figure out a way to do this. So in thinking about how to power random slopes, it depends on how many occasions you have, how far apart in time they are, how many people you have, how strong of a signal you have in terms of change over time, both of the fixed effect and a random effect. So you have to be able to come up with reasonable guesses for all of these parameters in order to simulate data to do an empirical power analysis. So I figured out a way to try and do this. There's a paper in Psych Methods that I recently reviewed that I hope comes out soon that has a really good tutorial on this, so be on the lookout for that. They did, I think, a better job than I did, but this is something that I developed for our own internal use at KU. So I have a document here, how to use this particular spreadsheet that I wrote up for my colleagues here. So first thing is to come up with a number for total variance. Doesn't matter what it is, I usually pick 10. It sets the scale of everything else to follow. Then we have to calculate what is known as the sum of squares with respect to time. So this is pulling from Willett 1989, which is a classic article that talks about this. And his formula is right here. If you can also back translate this into the number of occasions as well as just the variance in time, which is sums of squares divided by n. And you can enter that into the spreadsheet here. So if I have 7 occasions, for instance, that creates a sum of squares for time of 28. If I have 5, that would be a sum of squares for time of 10. So we'll stick with 7 because that's what I have here. Then it wants to know what is the variance of the level 1 predictor if it's not time. So I have a version of this that goes with time and a version of this that goes with not time, versus the variance of a level 2 predictor that you're trying to power. So the example that I have pulled up here is a 2-group example where we have equal sample sizes in each group. So if my mean of my variable is 0.5 for a grouping variable, I would say its variance is 0.25. So put that in there. And then the prediction section. It wants to know what you think a reasonable guess for the interclass correlation is. Well, those you can make reasonable guesses. And this is after controlling for time what the interclass correlation would be. So in this current setup, I have it set at 0.3. And you can change that to see how things change. That 0.3, given a total variance of 10, tells you how much your intercept variance should be and your residual variance should be. This should be 7, this should be 3. From there, given your sums of squares for time, which is dictated by the number of occasions and how far apart they are, and the residual variance that you just found, you need to make a guess for what slope reliability is. And this is also from Willett 1989. It's essentially the idea of reliability as true score variance over total, where the error part is conveyed by the residual variance. So if you can come up with reliability, which ranges from 0 to 1, you can invert the formula to figure out what the slope variance should have been to get to that level of reliability. So in the spreadsheet then, I was generous. I said time slope reliability of 0.6 only, so I set it kind of low. And then I have columns for a fixed effect predicting residual variance, which I gave a D of 1, a fixed effect predicting the intercept, which I'll switch back to 0 here, and a fixed effect predicting the slope. So this is the idea that the D for group differences in predicting the time slope would be translated into an R of 0.24. So you can go from D to R. There's a formula built in here to do that. So here's what the unconditional time model variances would be. I told you that we would have a residual of 7 and an intercept of 3, given an interclass correlation of 0.3. That creates a slope variance of 0.375 based on that amount of residual variance, the sums of squares for time, and the time slope reliability. So all I've asked you for in terms of guesses right now is to set the scale of this thing, which is arbitrary. How many occasions? Here's a formula for how to calculate sums of squares if they're equal interval, for instance. Take a guess for the ICC and a guess for the slope reliability. Then the spreadsheet calculates what the percent of explained variance would be for each, and thus what the leftover variances would be in the conditional model. So these are your variances left over if the fixed effects of your level 2 predictor are as you predicted. So it would have explained no intercept variance, so this would be like an intervention study where the intercept is equal across groups. It would have explained let's see, 6% of the slope variance. So there's the fixed effect for the effect of the group on the slope, and there's the leftover variance. So I've went from pulling numbers out of the air to creating model parameters. Then I stick them in a program. There's an R package, by the way, the Psych Methods article people made to do this, and I was like, oh, this would be the one time I would want to learn R. But this is M+. I'm using their Monte Carlo feature, which allows us to make up data. So what I'm doing is making up a data set that is consistent with those estimates. So I have a grouping variable. This is an SEM, so it's a single level, time 1 to 7. Cut points for group. This is on a probit scale, what the mean of the groups would be, which is 0 for a 50-50 split. I do the number of people in the sample. So let's say here I want 40 people total. This particular design is going to have 20 people in each group. The number of sample replications, let's do 500 to make it run fast. And you can set a random seed to make sure that you get the same results back if you want to share. And my random seed, as always, is Jenny, 8675309. Thank you, thank you. I'm here all week. Oh, wait. So here then, in the model population, I say, all right, my grouping variable has a mean of 0 and a variance of 1. So I'm putting it on the probit scale. This cut points thing up here tells it to make 2 values for it. I'm setting the intercepts for my observed variables to 0 because I'm going to have an intercept factor. Here's my slope factor, so this is a linear growth model. I'm setting the covariance between the intercept and slope to 0 because that likely doesn't matter, and the fixed effect to 0 because that doesn't matter. And then down here are the values that came from my spreadsheet. So given a total variance of 10, a variance of the level 2 predictor of 0.25, number of so I don't have to change too much. Yeah, 7, that's right. Excuse me. A residual time effect of d equals 0.1 and d equals 0.2 on the intercept and d equals 0.5 on the slope. These are the numbers that my spreadsheet told me to put in. So this is my intercept variance left over. This is my slope variance left over. This is the fixed effective time. This is the main effective group on the intercept, and this is the effective group on the slope. And then in the model, I set up the growth model as if I don't know what the answers are, but I provide the answers I put into the simulation as start values by putting the star here. And then I hit run. And it's done. Let me see if I can blow up the font here. Yep. So it spits back everything you told it. It spits back the means and covariance matrix for the first replication. So it did this 500 times. Here's all the fit statistics. We can ignore that. The thing I care about is right here. First column is what it was supposed to be in the simulation. Second column is what it was on average. This is the standard deviation across my samples and the average SE, so these should be about the same. The last column is the one I care about, percent significant coefficient. Percent of the replications in which that fixed effect or that variance was significant. This is empirical power. So going down to the stuff I care about, only 10% of the time would the effective group on the intercept that I put in be significant. And only 24% of the time do I have enough power to detect change differences by group if I only have 20 people in each group. So 20 is not enough. So I could say, all right, I didn't think 20 was going to be enough. How much do I need? What if I had 30 people in each group? So now I have 60. Slope on group is up to 31%. So from here, I fuss and fuss and fuss until this number turns into something like 0.8. Because normally people come to me and say, I can only get 30 people. What can I do? And so my answer is, all right, with 30 people, you have enough power to detect this much of an effect size with 80%. To figure out what this much is takes a little bit of iteration until you can get to this number. So you might try a little bit of range of intraclass correlation, a little bit of range of slope reliability, and then test different effect sizes until you get to the magic 0.8. So that's what I do. And I really don't like doing it, so I hope to train all of you to do it so that I don't have to do it anymore. There, and so I'm happy to send these things out if it would be helpful. How to go through this process. It's limited. I don't have this generalized to any kind of non-normal outcome yet. I also don't have it generalized to what happens when you have more than one predictor. So it's very limited in what I can do, but it should be relatively easy to generalize if you can anticipate how related your predictors are, then you can feed them into the model. So, how's that, sir? It just sets the scale of the DV. So this would be like, what's the total variance in my DV? If you know what it is and it's a number, then these parameters could all be relative to that. But ultimately, it doesn't matter, because if I change it, say, to 1, everything switches accordingly because it's all relative to that. So they're all based on proportions. An ICC is a proportion. A slope reliability is essentially a proportion. So it's the first number is completely arbitrary. It just sets the scale of the entire fictitious model. I like 10 because then I know that the intercept and residual variances are going to be round numbers. Yep, and that's what this spreadsheet was designed, was group differences in the slope. So here, for instance, with the current design of 7 occasions, a linear slope, and only 20 people per group, I don't have anywhere near enough power to find a D of 0.5 on the slope, which would translate into an R of 0.2. But if I bump that up to, say, a D of 1, that translates into an R of 0.45. The rest of the numbers would be bumped up accordingly. I feed those new numbers in, and I see if it's better. So it's the effect size is for the mean difference between groups in the time slope. That's what the D is for, because usually people give me Ds, and so I've got to convert them into Rs, which then can convert into variance accounted for in the slope, R squares. And that's where I get what the variance should have been, and then what it needs to be after being predicted by the group. So yeah, I would mess with this number until I get something that hits 0.8, and then I would say, yeah, with this design gives us power for D's predicting slope differences between groups of 1 or greater, and that's what I would have to say. So it's not technically a power analysis, it's more of a sensitivity analysis, because this design is fixed and you're just seeing what effect size you can get. But that is almost always what people give me. They've made these decisions ahead of time, or the real-world constraints they're in say they can only get this many people. So, other questions? So then do you want to take another break and look at cross-random effects models when we come back? Or is there any other requests? Okay, the request is for a break. I heard that one loud and clear. Let us do that then.